you ready? Are you ready? Oh, are you ready to go? Are you ready? Are you ready? Are you ready to go?
Now, sometimes it's impossible to list out all of the possible outcomes of something. So there is a multiplication counting principle that we can use here. In the second part of this, we'll be going into more elaborate counting techniques. But essentially, if we have m ways here to make a first selection and then n ways to make a second selection, the total ways of making the pair would be m times n. And if we have 3, 4, or 5 different selections, we could continue. So we'll look at a couple examples here. You're choosing an outfit to wear. That should be an outfit, not n, sorry. And you've got 5 different pairs of jeans and 6 different t-shirts. How many can you make? Well, we can pick from 5. We can choose from 5 pairs of jeans and 6 different shirts, so 5 times 6 is 30. So let's look at this example here that's a little bit more complicated. So we're trying to figure out how many different telephone numbers there could be with these set of rules. So we're going to be picking 7 digits, so let's make 7 spaces here. And so our first digit, it says the digit cannot be a 0 or 1. Now the digits are 0, 1, 2, 3, up to 9, so there are 10 digits. And for the first digit, we can't use 0 or 1, so there's 8 total digits. There's no restriction here, so we could have 10 digits, 10 digits, 10 digits, 10, 10, and then it says the last digit cannot be a 9, so we only have a choice of 9. So to find the total number of telephone numbers, we would multiply this together, and we're going to get 72, and then we've got 1, 2, 3, 4, 5 zeros. So there would be 7,200,000 different telephone numbers that we could create. We will be talking about something called permutations, which is when we are arranging things, and combinations when we are making or selecting groupings. We talked a little bit about counting principles in the probability video. We talked about the counting multiplication property or principle, and we'll be building that on that today. Some of the formulas that we use for probability use a new operator that may be new to you called the factorial operator. It's the exclamation point. It's a math operator, and the way it works is the number, it follows the number, and to evaluate that, you take the number and multiply it times all the numbers starting there down to 1, and you would multiply that string of numbers together. So for example, 6 factorial would be 6 times 5 times 4 times 3 times 2 times 1, which is 720. Let me bring a graphing calculator on here to show you how to do it on the calculator. Now it may get tedious if we had a big number to do a factorial, so let's look at maybe 11 factorial. So type in the 11, and the stuff we're going to be using today is in the math menu and under probability. So I'm going to go over to probability, and the 4th item there is the factorial operator, or the exclamation point. And now we just press enter, and you can see that factorial numbers build up quite quickly here. So this is a big number when we did the 11 factorial. So we're going to be talking about permutations first. They are arrangements, and we are selecting from a group of items, a pool of items, of n items, and we're pulling out a subset, r items, and we're arranging them. So the order in which they get selected or get placed makes the difference. Again, the key point when you're trying to decide between permutations and the next thing, which will be combinations, is does the order matter? Is it important? So for example, if we are arranging the 4 letters from the word math and seeing how many different words we can make, the order would matter. So this and I'm using the term word loosely. It's just we're just using it as an arrangement of the 4 letters taking up these letters. So math is different than this. So those would be 2 different permutations or arrangements. What we're interested in is being able to count or find the total number of arrangements that can be made in different situations. So this is the notation we will use for permutations. So NPR is saying how many ways can you arrange R items that are pulled or taken from N items, or another way of saying that, as I said here, we're arranging N items taken R at a time. This is the terminology. This is the formula. See, it uses this factorial notation. So for example, if we had 20 runners competing in a, say, a cross-country race, and we're going to give 3 medals or ribbons, gold, silver, and bronze. So as you know, winning the race is different than coming in second or third. So this is a permutation problem. And we're looking at how many different finishes could there be. So this would be, the pool of numbers is 20, and we're arranging 3 at a time. We're arranging gold, silver, bronze. And if we plug into our formula, we would get this. Now, we would have, this would be 20 on down to 1, and this would be 17 on down to 1. So every number from 17 all the way down to 1 all cancel out, so we're left with this. So this looks very familiar to that multiplication counting property that we used in the previous tutorial. Now let me bring a calculator up here and show how we could calculate that using the graphing calculator. Now to do that, we're going to enter the N number first, so I'm going to enter 20. And then we're going to press the math button here, and then go over to the probability matrix, the probability menu, and NPR, our permutations, is item 2. Now we enter the R, which is 3, and press enter, and we get the same number here that we had when I did it by hand. So we just described how to use the calculator. So let's look at another example here. So let me bring the calculator back. We've got let me read the problem. We've got 15 people, and we're forming committees, and you know, the different committees would have different leadership positions, so the order does matter. So to do this one, it's going to be 15, and it's a permutation because we are assigning roles. So we need math button again, go to the probability menu, select item 2, and now we're selecting 3 people, 3-person committees. So let's put the 3 in there. So there would be 2,730 different committees that could be formed. Now, when we're using permutations, if some of the items in the pool that we're selecting from are duplicated, then we have to account for that, because in the arrangements using the first A and the fourth A from a permutations point of view, those are treated as different letters, but since they're the same, we have to remove or divide out the duplicate arrangements. So we get this formula here. It could be extended if there were 3 objects that were repeated. We would have another factorial thing on the bottom. So if we want to figure out how many arrangements for banana, we've got 1, 2, 3, 4, 5, 6 letters total, so that's our N. We've got an A that's repeated 3 times, so that would be R, 3 factorial, and we have 2 N's. So again, you can see here that we would do this calculation here, and there would be 60 different arrangements. If this had been a 6 letter word and none of the letters were repeated, this would be a 6, and then math probability NPR, and we would say, let's say we're using all 6 letters each time, we would have 720 possible arrangements. So because of the duplicated letters, there are fewer arrangements that we can make. Now let's switch gears to combinations, our groupings of items. In this case, the order that we select does not matter. And so it builds off of the permutations formula, but we have to remove our duplicates. So that's by dividing. Now, most of the time in our class, we're going to be using the graphing calculator to calculate this. So your main decision will be deciding, is it a combination or a permutation problem? So here's an example of a combination problem. We're picking 3 students, or it's like the committee problem, for an exemption. But in this case, whether you are picked first or third, you still get the same treatment. You still get the exemption. So this is a combination problem. It would be 29 C3. Using the formula I showed, this is the way we would calculate it. And again, using the calculator here, we would do 29. Math, probability. This time we're going to use combinations, number 3. And there are 3 people that we're selecting, or 3 in the group. So we have 3,654 different groupings that we could choose. Now, one of the reasons we want to be able to count things is because when we are doing probability, we need to know number of outcomes and total number of outcomes, success outcomes, etc. And sometimes it may be too many of them to list by hand to count, or it'll be error prone. So we can use combinations and permutations to accomplish that task. So in the example, we've got a club that has the set of members that I listed here. And in our first example, we're going to be picking a council. In this case, the first person chosen will be the president, second the VP, and third the treasurer. So since we have positions assigned, this is going to be a permutations problem. And we want to know the probability that this one person will be chosen as president. So we need to know, in terms of the success outcomes, it would be how many different committees could be formed, or councils that could be formed, where Ichabod was chosen first, and then 2 of these other people were chosen in the other order. And then we needed to divide that by the total number of councils that could be created. So if we look at that, the councils where Ichabod is president, the total number of councils, I messed up here. So again, the total number of councils where Ichabod is chosen first. So we're choosing Ichabod first. That's 1. And then that means there are 10 people left to choose from for the second position. And now we've got 2 people on the committee and 8 here. So we're using that multiplication counting principle here to figure out our number of successful outcomes. So there are 72 councils that have Ichabod as president. And then we need to know the total number of councils, and that would be 10 people being chosen 3 at a time, and it's an arrangement. And we could do this in the calculator, and we get 1/10. So there's a 0.1 probability that Ichabod would be chosen president of this. Now let's look at our last example. In this case, we are using combinations. We want to know what's the probability that Ichabod will be chosen for the council. So we know that Ichabod will be chosen to be successful, and then we have groupings of 2 other people. So this would be 1 for Ichabod times the number of groupings of people not counting Ichabod. So that would be 9C2 because we're not counting Ichabod. And then the total number of councils would again be 10C3. Again, in this particular case, we don't care about leadership positions. And so we get 3 out of 10. An application of combinations not dealing with counting things or probability is the binomial theorem. In the binomial theorem, we are working on how to expand a binomial to an integer power. And using the binomial theorem, we can do that fairly easily. So what I mean by a binomial, we've got two expressions added or subtracted in a parentheses raised to an integer power. When we do this manually, remember we have to turn this into a plus b times a plus b times a plus b repeatedly and use FOIL and the distributive property. And we've done some of those in class, and it's quite tedious, especially when the powers get bigger than 3. Right here is the binomial theorem. So we're adding a bunch of terms, and in each term we have a combination here. So in items, so the number of items we're taking combinations is the same as this exponent, and then as we go across, the number of items we're selecting are 0, 1, 2, on up to n. The exponents on the first part of the expression start at n and count down by ones until you get to 0, and the second term we start at 0 and count up to b. So we'll do an example in a minute. Now, related to the binomial theorem, because we've got to determine all these combinations, we've learned how to do that in the graphing calculator, but that gets to be a little time consuming. A French mathematician named Pascal found an interesting pattern related to combinations. So he arranged combinations in this triangle. So in the first row, we've got n equal to 0. So in the first row, we've got n equals 0. Second row, n equals 1, n equals 2, etc. And it could keep going. And we go across with our, NCR, the R values going from 0 all the way up to n. And he's arranged this into a triangle. Now, in the next slide, we're going to calculate these, and we're going to see there's an interesting pattern so that we can calculate this triangle as long as we start at the top and go in order without using a calculator. So let's look at that. So if we start at the top, 0C0 is 1 if you use the calculator, and the next row we have 1 and 1. Now all the way down, the edges will be 1. Once the inner numbers, we will take the two numbers above it and add together. So if we calculated that, I just wrote that number there. If we calculated 2C1 using the formula for combinations or the calculator, we would get 2. So our next row is going to be 1. Now we add those two numbers. We add those two numbers, and then we always end with a 1. So this is n equals 0, 1, 2, 3. So let's do 4. We would have 1, 4, 6, 4, 1. And we do the last row here, the fifth row, 1, 5, 10, 10, 5, and 1. And we could keep going, 1, 6, 15, 20, 15, 6, and 1. Now we can use those numbers when we are doing a binomial theorem. So let me highlight these numbers and copy these over to our next page here. So let me put these over here. It's not letting me do that. Let's try here, see if we can paste it here. All right, so we got our numbers. Let me move these out of the way. So now we're wanting to, expand this. So remember the binomial theorem for this. If I write, let me just write out, take the time here, it'll take a few seconds, but this is going to be 5, C0 times the first a, which is x to the 5th power, and then negative 2 to the 0 power. Now we're going to have 5c1 x to the n minus 1, so 4th power, and negative 2 to the 1st. And then we've got 5c2 x to the 3rd, negative 2 squared. I'm going to have to go on an angle here, sorry. And plus 5c3 x squared, negative 1 cubed. So the b exponents are going up by 1, the x's are going down by 1. It's going to be x to the 1st, negative 1 to the 4th, and then our final term here, 5c5 x to the 0 power, that's a 0, and negative 1 to the 5th. So now we can evaluate. So we can get the numbers for all these combinations looking at our row here, for n equals 5. So if I fill in, I've got 1 x to the 5th times, now negative 2 to the 0 is 1. Now you could be simplifying these in your head. So now we've got 5 x to the 4th times, now negative 2 to the 1st would be negative 2. Now we've got the next term, 10 x cubed times negative 2 squared would be 4. Now we've got 10x squared times, this should have been negative 2, negative 2, negative 2, sorry for that. So negative 2 cubed is negative 8. We go down here, so plus 5x times negative 2 to the 4th, which would be positive 16. And lastly, 1x to the 0 power, which is 1. Remember, anything to the 0 power from our exponent properties are 1. So we have 1 times negative 2 to the 5th, which would be negative 32. So now we simplify here. We have x to the 5th plus, or that's not going to be plus, that's going to be subtract, because we've got negative 2 times 5. Now we have 4 times 10, so plus 40 x cubed, negative 80 x squared, 5 times 16, so plus 80 x, and then minus 32. And that is our answer for expanding out this expression to the 5th power. Again, I wrote all this out, so it took a little bit longer. We could have taken a little bit of shortcut by knowing the theorem and doing some of these calculations in head. And you can see this is a lot faster than foiling everything out 5 times or 4 times. So have a great day and talk to you later.
Are you ready? Are you ready? Oh.